Thanks, Gordon, for that introduction. And thank you, Brenda, for asking me to come this evening to speak to the Natural History Society of Northumbria. It's a great pleasure to be here. As you can see, I'm going to be talking about work which is really a team effort. Andrew Bagley, who is a colleague of mine in maths, stats and physics, Andrew and I work with a postdoc, Hannah Krajcek, and Miguel Morales-Maqueda, an academic in School of Natural Environmental Sciences, and I were, a few years ago, the supervisor of a PhD student, Alethea Mountford. So the work I'll be talking about will, on occasions, draw on some of this team effort that we've been carrying out on microplastics. Now, I think with the advent of the Blue Planet 2 documentary, I think it really highlighted to the world the terrible plight of the oceans when it comes to pollution by plastics of all sizes. There's nowhere in the world ocean where you won't find microplastics. So going from the Arctic basin all the way down to the marginal seas around Antarctica, the Weddell Sea, the Ross Sea, the Bellinghausen Sea, microplastics are ubiquitous. It really is a very sobering thought. And one might wonder, is there anything that one can do about the pollution that we've put into train ever since we started to manufacture plastics? So towards the end, I want to briefly look at that, and I'll invite you to help me think of some strategies which might relieve the ocean of their load of microplastics. Okay, so what's in store for this evening? I'm going to begin by saying very briefly, what are microplastics? How do they enter the marine environment? Once they're in the marine environment, what happens to them? I'll say very briefly, because I'm sure many people here know more about this than me, what the impacts of microplastics are on marine ecosystems. And then finally, I'll wrap up with a few thoughts about potential cleanup strategies. Okay, so the types of plastic in the ocean. We have the larger plastics, which we'll call the macroplastics. They range in size from about 5 millimeters up to many meters. And some examples of macroplastics are shown in those diagrams on the top right-hand side. They can range from plastic bags, toothbrushes, cups, tires, you name it. And then down at the smaller scale, we have the microplastics. More specifically, their size ranges from a few millimeters, 5 millimeters typically in the literature, to 100 nanometers. And there are two sources of microplastics in the ocean. I'll talk a bit about that in the next slide. And then below microplastics are the really almost infinitesimally small plastics called nanoplastics. And in terms of detection, well, the sheer scale of them means that trying to get a handle about where they are, their density distribution in the ocean, is currently impossible. Let me just highlight the horrendously long lifespans of materials, plastic materials, that enter the ocean. I mean, the basic picture you can see here is the lifespan is long. We're talking decades, hundreds of years. And this is accredited from NOAA, US National Oceanic and Atmospheric Agency. Goodness knows what the state of NOAA will be under the Trump administration. I suspect their budgets are going to be highly constrained over the next 4 years, which is a great pity because they do a fantastic job, I think, in the public outreach of their science as well. So let's just keep our fingers crossed that NOAA can survive the next 4 years. So the message here is that the materials, the plastics, fishing lines, plastic bottles that enter the ocean, non-plastics, aluminium cans, they are going to be around for a long, long while, decades to hundreds of years. Okay, I mentioned 2 slides ago that there are 2 sources of microplastics. The first is what we call the primary microplastics, less than 5 millimeters when produced, and they include microbeads, which are found in cosmetics, they're found in sunscreens, they're found in toothbrushes, toothpaste. And then there's also another typical source of microplastics are the fibers from your fleece jackets when you wash them. They unfortunately get flushed down through the waterways and ultimately into the sea. Then we have the degradation of larger plastics cascading down in size to the microplastic regime. So what happens is that larger plastics, when they're in the marine environment, they're exposed to UV sunlight at the surface, and over time that makes the plastics brittle. And once they become brittle, then through the combined action of the wind and the waves, that physically breaks down those larger plastics into smaller pieces. And ultimately, there's a size cascade right the way down to the microplastic regime. Okay. I want to show you about a 3-minute video again from NOAA, which I think very nicely gives you a good overview of the problems of microplastics, or all plastics, in the marine environment. So over to NOAA.
Plastic is everywhere. A lot of it ends up in the ocean. Most plastics in the ocean break down into very small particles. These small plastic bits are called microplastics. Other plastics are intentionally designed to be small. They're called microbeads and are used in many health and beauty products. They pass unchanged through waterways into the ocean. Aquatic life and birds can mistake microplastics for food. Research is being conducted, but there's much we still don't know. In 2015, the U.S. banned the use of microbeads, but microplastics are still a huge problem. You can help keep plastic out of the ocean. Remember, reduce, reuse, and recycle.
So I think that very nicely summarizes what I've had to say so far about the sources of microplastics. The final slide there, with the final message, I think is really important. Once plastics find their way into the marine environment, it's one devil of a job to remove them. So over the next few decades, I hope that the governments of the world will try to firstly remove the use of single-use plastics and ban ultimately the production of all new plastics and try and recycle. We want to try and prevent plastics entering the marine environment, because once they're there, as I say, it's one devil of a job potentially to come up with any viable strategy to remove them. Okay, so let's move on to the question of how do microplastics find their way into the ocean? So terrestrial sources account for 80% of marine debris, and the ways that these terrestrial sources of plastics ultimately get into the sea is through things like river and sewerage outflows, and perhaps through the effects of winds. I mean, we've had 2 notable storms recently in the last week, and you can imagine, you can see just driving or walking around how much litter is suddenly generated by the action of strong winds. Well, ultimately, a lot of that plastic gets just blown into the sea directly. So wind, but in general, wind does carry much less plastic into the ocean than rivers, except I've said in extremely windy areas, and I've just pointed out that when we have severe storms or hurricanes, then that leads to an enormous potential spike of direct input of plastics and other pollutants into the coastal seas. In the last 10 years, work at Plymouth University has really also highlighted the source of microplastics from vehicle tyre wear. And as the tyres roll, the tyres degrade through the physical effect of friction of the tyres on the road surface. And then that tiny pieces of plastic or rubber compound from the tyre ultimately can get washed off the road into waterways and eventually find their way into the marine environment. Tyre wear could account for 65% of all microplastics released to UK surface waters. And in fact, globally, as I'll show you in the next slide, tyre wear is likely to become an even greater source of plastic into the ocean. You know, there are about 1 billion cars on the planet today, and by 2040 that could double to 2 billion. And here this schematic just highlights how through tyre wear, little black dots, if you like, schematically show the wear of tyres through rolling on the surface of the road, how those little bits through wind effects, through wastewater effluents, and through runoff from the carriageway from the road takes that those plastics, that material, and eventually inputs it into the coastal seas. There are also ways in which plastics are directly input into the marine environment. One obvious one is from fishing activities, nets and lines which can become discarded. How many times have we walked along the beach and seen discarded lobster pots, fishing lines, etc.? So we know that this is a significant source of direct input of plastic into the ocean. Also, increasingly, the activities of aquaculture lead to an input of plastic into the ocean. And I've shown schematically how this comes about here through weathering of nets and containers. Feed packaging can sometimes find its way or be discarded into the locks where or the pens where the fish are being farmed. Ships and recreational vessels also contribute to the direct input of microplastics or plastics into the ocean. For example, typically 1,700 shipping containers are lost at sea each year. So I've mentioned that river inputs is a major conduit for carrying terrestrial plastics into the marine environment. This map, colour-shaded map of the Earth, shows you the countries which are responsible for the largest inputs of plastic through their waterways into the ocean. I guess it probably comes as no surprise that the so-called hotspots are the subcontinent of India, China, Indonesia. I think rather soberingly, if you look at the UK, amongst the European countries, we come out rather badly on this picture. I feel very embarrassed every time I see this, that we actually are a significant, within northwestern Europe, a significant source of plastic into the ocean. So, once the plastic has found its way, by whatever pathway, into the ocean, what happens to it then? So let's firstly get an overview about the quantity and properties of the plastic that enters the ocean. About half of the plastic, clean plastic that enters, is buoyant, i.e. it floats. Okay, so how much buoyant plastic do we estimate has gone into the ocean since, say, around about 1950? Well, the figure is just mind-bogglingly large. I said it's 57,000 million kilograms. Now, I just can't imagine how to relate that to something perhaps more that we can appreciate. And I just was looking up today, what is the typical weight of an adult blue whale? And if you convert this huge amount of plastic into the numbers of blue whales that is equivalent to that in weight, it turns out it's slightly under 500,000 blue whales in weight that's gone into the ocean. And of course there are significant error bars in all of this, because getting the data is tricky out there, right? Observing what happens to this stuff once it's in the marine environment is challenging. About 60% of the floating plastic waste has been washed from the coastal seas into the open ocean. But yet, and fascinatingly, if you do an audit, the best you can, from satellite and ship sampling, to find out how much floating plastic is in the world ocean today, it's only about 1% of the buoyant plastic that initially entered. In other words, there's a whole load of plastic that's buoyant when it entered the sea that's not there today at the surface. It's gone. So the question is, where is the missing floating plastic? And that's one of the things that our postdoc and Andrew and I have been looking at from the point of view of mechanisms for removing that plastic from the sea surface. Before I tell you a little bit about that, let's just remind ourselves where the reservoirs for marine plastic are. Once this sort of gets into the sea, where could it potentially be? Well, I think we all appreciate that there's far too much plastic sitting on the shoreline. It also resides in our coastal seas. Some of it floats on the ocean surface in the ocean interior. Some of the plastic is not on the bottom of the sea floor, not at the surface, but it's within the water column. And some of that plastic does, by a variety of mechanisms, reach the sea floor. If the sea floor is sandy, has lots of sediments, it doesn't take very long through the action of waves and currents, deep currents, abyssal currents, for that plastic to get buried. So trying to estimate precisely how much plastic has reached the sea floor is challenging, even with deep robot submersibles. Let me talk very briefly about something that many of you may have heard about in the news, about the so-called floating garbage patches of plastic in the ocean. How do they come about? Well, if we look at the typical winds that blow across, say, the Atlantic Ocean on the left-hand panel here, in the near equatorial regions, you have trade winds blowing from east to west, shown by those two bold arrows. At mid-latitudes, further north, the winds are predominantly from west to east. So it comes as no surprise then that through the action of the winds, that there is a surface circulation of waters shown in those arrows in a clockwise sense. In fact, the way I've shown that schematically suggests that this closed circulation, it's called a gyre in oceanography terms, it looks perhaps as if it's symmetric. Interestingly, the gyre in reality is not symmetric in the sense that the currents on the western side of the closed circulation are much stronger than on the eastern side. And you perhaps would recognise that those strong currents on the western side are, in the case of the North Atlantic, attributed to or known as the Gulf Stream. So you've got this circulating, we call this subtropical gyre. Now, through mechanism that I won't go into the physics of it, but it turns out that the upper surface waters in that gyre tend to move to the right of the circulation. In other words, the upper waters tend to move towards the centre of the gyre, and then the waters downwell and sink. So any material, plastic or whatever it is, that finds its way into a subtropical gyre will be drift towards the centre of the gyre and get trapped there. And that's the origin. This drift, by the way, for those who may want to know technically what it's called the Ekman transport. So that gyre then leads to the trapping of buoyant materials, whether it be plastic, timbers, whatever it is, into the interior of the gyre. And it's in those regions that you find the garbage patches. And if you look at a global view of the world ocean, there are subtropical gyres then in the South Atlantic, of course in the North Atlantic, in the Indian Ocean, and in the North and South Pacific basins. So I guess you could say, well, we can easily go out and perhaps go on, send out, whether it be manned vessels or whether it be robot surface vessels, wave gliders, and you could perhaps hoover up all of the plastic in those subtropical gyres. After all, it's at the surface, trapped within the subtropical gyres. I have no problem with that, except that, recall what I said a few minutes ago, that it's actually only a tiny amount of the plastic that we've input into the ocean that's actually at the surface. Most of it is elsewhere. So I guess it's you could say it's better to start somewhere and just address the surface floating plastic and try and remove that, and I wouldn't argue with that. But let's not kid ourselves that it would address the issue of plastic pollution in the ocean. Another reason why plastic doesn't sit at the ocean, even if it's initially buoyant for very long anyway, is the following. It's called biofouling. And these panels on the left-hand side really nicely show in a laboratory setup how biofouling progresses. So biofouling is essentially the growth of organisms, algae, other marine plants on the surface of a material. In this case, it could be plastic. And if you look at the progression of biofouling on a piece of plastic, as shown, look at C, D, E, all the way through. C is relatively clean. You can see the brown, darker brown patches of algae growing on the surface. By H, it looks like the beetle's hairdo there. It's become really hairy and very, very, very overgrown with materials. So that's the process of biofouling. And it plays a significant role in the fate of clean, buoyant plastic that finds its way into the ocean. And, here's some examples of relatively clean, buoyant plastic sitting there in the upper metre or so of the ocean. Okay, so what is the impact then of biofouling on initially buoyant plastic? So let me show you through this cartoon or schematic. So the red dot is our clean buoyant plastic, and it's floating around there, And of course it starts to experience biofouling. And as the biofouling increases, it can tip the density of the composite, the plastic and its growth around it. It can tip it from being a buoyant body to one which is no longer buoyant. In other words, it's denser than surrounding seawater, and it starts to sink, as shown like that. Now, as the biofoul plastic bead, if you like, starts to sink through the water column, two things will happen. As it starts to sink, the amount of sunlight, of course, that penetrates the water column starts to fall off with depth, and as that bead starts to sink, it starts to move into the twilight zone, and if it keeps sinking, into the darker zone. And think about what you need for plant life, or any sort of plant life to flourish. You need some photosynthesis, you need some light. So as it starts to sink into that darker region, then the rate of biofouling naturally tails off. In addition, of course, as that particle sinks, it starts to experience higher pressure, okay, because of the weight of the water above it. And some organisms which are happy to exist at the sea surface at atmospheric pressure are far from happy to live in a region where the atmospheric pressure, or where the pressure is many times above atmospheric pressure. So the combination of falling light together with increasing pressure as the particle sinks leads to either the removal and or the switching off of biofouling growth. And when that happens, then the particle can start to regain its buoyancy, and it starts to rise back up to the sea surface. And in the literature, this is now known as the mechanism for the plastic yo-yo. And therefore the biofouling plays a role in the removal of initially clean, buoyant plastic from the sea surface. Hannah Krajcek and Andrew and I developed some mathematics to describe the plastic yo-yo. And this diagram shows the fate of a plastic particle in the Arctic region at 70 north. It shows the fate of a clean plastic particle. Initially it starts off in January the 1st, and it shows the fate of this plastic particle, i.e. its movement in the water column, over a full year. And of course, at such a high latitude, during the winter months, there's no sunlight at all. And so there's no photosynthesis, there's no biofouling or any significant biofouling at all. So during the first couple of months, the particle sits nicely at the sea surface. And then, as the sun rises above the horizon, biofouling kicks off, and you can see, I won't go into the complicated years of why, but it starts to obviously undergo these oscillations, the plastic yo-yo. Interestingly, the oscillations are subsurface for a while, and then towards the end of the oscillations in the late spring or early autumn, those oscillations are from surface to depth, and that's a sort of a typical behaviour of a plastic particle in an ocean which is stratified, i.e. the water column is denser as you go down, but there's no ocean currents in this. So it's a really simple toy model, but it nicely captures, for example, at high latitudes, the sort of behaviour that one might expect from what is initially a clean, buoyant plastic particle. We've looked at this at other latitudes. No time to talk about that in today's talk. But there is the plastic yo-yo in its cleanest, simplest example. Okay, so on this one, I want to show you something that my colleague Miguel and our PhD student Alicia Mountford did in terms of a computer simulation of non-buoyant plastic flowing out through the major rivers around the world. Where does it end up? Now, it's quite a slow video, so I'm going to speed this up because otherwise you'll be here all night. So let me speed it up a little bit, and you can start to see, this comes as no surprise, I guess, that, the largest amounts, this is non-buoyant plastic, no biofouling. So once it's in, it sinks, and then it moves with the ocean currents. But of course, most of this non-buoyant plastic shown by these colours starts off from India, around Southeast Asia and China. Significant amounts in the Mediterranean. When it comes out through the Mediterranean, it comes out and deflected to the left, down and into the Gulf of Guinea here. And as you carry on, well, we won't go through in the so-called computer real time. We'll get to the end. And you can see here, this is the distribution then of the non-buoyant plastic in the ocean after probably about, I think about 30 years of simulation. Lots of things that aren't in this, including the biofouling and tides, but again, it gives us a handle on the sorts of behaviours that we might expect to see of plastics in the real world. And bear in mind, as I said, observing this stuff is quite tricky. So there is an important role to play for accurate or models which have predictive capability of where microplastics will go once they find their way into the ocean. Where are the hotspots? Where are the places with the highest concentration of microplastics? Could be on the seabed, it could be in the water column, and as we know, it's also at the sea surface in the subtropical gyres. Okay, so we've done that one. I mentioned to you that plastics find their way to the, if you like, extremities of the world ocean, the polar regions. For example, in the Arctic basin. How do the microplastics get into the Arctic? Well, the answer is through the transport by what's known as the global, called the conveyor belt. Let's just call it that. And let me just very briefly explain what this is. The red shows surface relatively warm currents. So in the North Atlantic, we have this warm drift of water up past the UK, up into the Greenland Sea. Now, once that warm water reaches the Arctic or subarctic basins, then there are two ways in which that water will become dense. One is simply through the cooling of that water at high latitudes. If you cool water, it becomes more dense. The other is, of course, that up here, in the wintertime, you get sea ice formation. When you form sea ice, if you look at a block of sea ice, the salinity of the frozen water is way below the salinity of seawater. It's only about 9 parts per thousand, whereas seawater is typically 30 parts per thousand. So when you freeze seawater, brine flows out of the matrix of ice crystals into the water below, and when you add salt to water, you make it dense. So the combination of cooling and salt input through sea ice formation makes that relatively warm surface waters dense, and then they sink back down as a deep western boundary current in the Atlantic and round into the Southern Ocean. Some of it goes into the Indian Ocean basin and upwells, some of it gets into the Pacific basin and comes up to the surface, becomes a warm surface water current, and back it goes. So that's, if you look at the ocean currents and average them over hundreds of years, that's the sort of picture you would see. We call that the conveyor belt. And you can see, therefore, that this is a mechanism. If you have plastics entering the surface around the Mediterranean, Europe, or elsewhere, over here in Indonesia through flow, it's a way of ultimately this conveyor belt of transporting the plastics into the Arctic basin. And that is a key reason why it gets into the Arctic. Okay, let's briefly think about the impact of plastics on marine ecosystems. So the microplastics are known to impact the organisms at the base of the marine food chain, i.e. plankton and zooplankton and fish larvae. Excuse me. How does that happen? Well, there are three key ways that I understand this happens. Firstly, there are physical effects. If you've got a small zooplankton, like a little prawn, and it swallows relatively buoyant microplastic, two things can happen. It's going to get terrible stomachache and constipation. Secondly, the amount of plastic it swallows is fairly significant compared to its body mass. So when it swallows relatively buoyant microplastic, it upsets the overall buoyancy of the poor swimming organism, and the thing starts to have real difficulty swimming in the direction it wants to. So that's the physical effects that occur if, say, zooplankton ingest plastics, less or buoyant plastics. Secondly, the plastic itself could be toxic to the organism. And thirdly, it could impair reproduction of the organism. Larger plastics like discarded nets, lobster pots, fishing lines, we know from some of those very emotive pictures and film that we saw in Blue Planet 2 and other documentaries, can ensnare and entangle marine mammals, turtles, dolphins, and leads to their demise. So it's that's a very emotive and very well known and unfortunate way in which larger plastic has a severe impact on marine ecosystems. Okay, so we're now coming to the final section, which is some reflections on cleanup strategies. From what I've just been telling you this evening, I wonder if any of you have got any ideas about cleanup strategies? Any ideas what we might do? Yes?
I was Holmes lectures a couple of weeks ago. Jeff Neesham, the professor,
oh, yes.
And he was talking about fishing nets anyway, but putting the sondes on top of the fishing nets.
Yes.
Actually obliging people to do that, so they have to transmit their position. So I thought that was very
So the marine mammals and some fish will keep well clear or some of them.
well, I think it's to fight, if there's any that dropped, that you can retrieve them.
Yeah.
Yeah.
Any other ideas about how we might attempt to clean up? Yes, lady at the back.
Not so much cleaning up, but preventing. So for washing machines for microfibers, you can now get filters to put on the outflow pipes.
Yeah.
And in some countries, they're actually going to be mandatory for all new washing machines.
I think that's a great news. Of course, you can imagine they require us to maintain and clean the filter. Otherwise, we'll have overflowing washing machines, won't we? Okay, thank you for those suggestions. The first one is don't let the plastic get into the sea in the first place. A colleague of mine, Eric van Siebel at Utrecht University, who gives many public outreach talks on plastics in the marine environment, says the following: picking up the rubbish while it's on land prevents it from continuing on a long journey through the oceans and falling apart into thousands of pieces of microplastics. It limits the time plastic can cause problems at sea and prevents plastic ending up on our plate. Let's try and persuade through all the links and powers that be to get rid of single-use plastics and reuse and recycle the plastics we produce and prevent them from getting in the sea. So that's not a clean-up strategy. It's trying to stop the problem of plastic pollution in the marine environment getting worse. So reduce our plastic use and dispose in an environmentally friendly way. Of course, there are biodegradable plastics now finding their way to commercial use. It's unclear to me, though, as they break down, whether there might be an Achilles heel in terms of toxicity to certain marine ecosystems from the breakdown of these plastics, biodegradable plastics. Now, the whole point of doing any sort of mathematical modelling of where plastic goes once it enters the sea is ultimately to ask the question, are there likely to be hotspots where the concentration of plastic is high? For example, yes, the subtropical gyres, surface subtropical gyres, we know there are garbage patches. Are there going to be places in the water column in certain basins where there's quite high concentrations of plastic? Similarly, on the sea floor, are there hotspots where plastics tend to congregate? For example, we know the answer to the latter question is yes, in things like trenches, even in the deepest parts of the ocean, Marianas Trench, we know that plastic finds its way just simply under gravity, cascading down into the deepest basins of the ocean. So if you can find the hotspots in the water column, on the coast, at the surface, on the seafloor, then arguably you might want to target those as places where we put some effort in trying to remove them, remove the plastics. So I've said the subtropical gyre garbage patches, and then I've just mentioned here why it's worth at the moment, because it's difficult, isn't it? Going out, you imagine trying to observe plastics in the water column once they've gone into the sea. It's an expensive and difficult thing to do, even with our range of marine robotic subsurface vehicles. Okay, so I've reached the end of my talk. Thank you very much for your attention, and I'll be very happy to take questions from you.